We physicists have waited 100 years since 1916 for this photograph.
Black holes are one of the most enigmatic aspects of our universe. To begin with, they aren't really objects in the conventional sense. A black hole is the result of an extreme warping of space and time, and because of that warping, a cascade of bizarre phenomena begins to unfold around them. Phenomena strange enough to fundamentally change your perspective on how the universe works. Some of it sounds like pure fiction, light bent like a thread, time slowing to a near standstill, matter stretched into spaghetti between tidal forces. Hearing it described, you might be skeptical, but behind these stories lies a rock-solid mathematical foundation, the equations of Einstein. The solutions of Schwarzschild and Kerr, backed by a growing mountain of sophisticated observational evidence, showing that the math matches reality. We're no longer talking about laboratory hypotheses. We're talking about the very real shadows weighing down the centers of galaxies, about gravitational waves that ring space-time itself, about the glowing, red-hot rings around the edge of darkness that our radio telescopes have actually photographed. Black holes come in many sizes. The lightest ones we've observed are a few times the mass of our Sun, with a reported record holder weighing in at a lightweight 3.8 solar masses. At the other end of the spectrum, supermassive monsters weigh millions to billions of solar masses, so large you could fit our entire solar system inside their event horizon. These behemoths have existed since very early in cosmic history, acting as the heavy anchors around which galaxies spin. But the black holes being formed today emerge from a process that is, by cosmic standards, quite ordinary: the life cycle of massive stars. From its birth, a star is a constant tug-of-war between two immense forces. On one side is gravity, the relentless pull, drawing everything inward toward the center. On the other is the outward radiation pressure generated by nuclear fusion deep in the core, where hydrogen nuclei are crushed together to form helium, releasing enormous energy. This energy pushes outward, counteracting the star's own weight. As long as these two forces remain in balance, the star continues to shine. But as the hydrogen in the core runs low, if the star is massive enough, the core begins fusing heavier elements: carbon, neon, oxygen, and then silicon. Each step up this fusion ladder creates a new shell in the star's structure, like a cosmic onion with many layers, each layer a reactor. This entire process generates energy, until it reaches a fateful threshold: iron. The problem with iron is that the energy equation flips. Fusing iron doesn't release energy, it consumes it. When a sufficiently large iron core builds up, the outward pressure fails, and the balance tips decisively in favor of gravity, like an anvil that suddenly loses its support. The entire mass of the star collapses inward in a brief but catastrophic moment. This collapse force rebounds, creating a shockwave we call a supernova, an explosion that can outshine its entire host galaxy for weeks. After the explosion, the fate of the remnant depends on its initial mass. If the star wasn't heavy enough, the quantum pressure of its neutrons can halt the crush, leaving behind a neutron star, a tiny, city-sized sphere so dense that a single teaspoon of its material would weigh hundreds of millions of tons on Earth. But if the mass is great enough, every known force in classical physics is overwhelmed. The collapse continues into a region that general relativity describes as a singularity, and a black hole is born. The universe can also grow black holes from smaller seeds, letting them expand by consuming matter and merging with others. It's also possible that in the early universe, massive clouds of gas collapsed directly into large black holes, skipping the stellar phase entirely. Whatever the dominant mechanism, the common thread is this: wherever matter is compressed too densely, space-time bends until a region of no escape is formed. But what exactly is this invisible wall that marks the point of no return? When you see a picture of a black hole, a perfect black sphere, remember this: the black part isn't necessarily the black hole itself. The true form of a black hole, in the classical description, is the singularity, an infinitesimally small point where the curvature of spacetime becomes infinite. The reason you can't see the singularity is because it's cloaked by a mathematical boundary, the event horizon. Einstein wrote the equations describing how mass and energy bend spacetime. Building on that, in 1916, Carl Schwarzschild found the first solution for the gravitational field of a symmetrical, non-rotating, uncharged object. His solution showed that if a mass m is compressed within a radius smaller than the Schwarzschild radius, Rs C22 gm, then a surface exists around it from which nothing, not even light, can escape. That surface is the event horizon. When you look at a black hole, what you are really seeing is the edge where all light rays trying to escape have failed. Even more peculiar, black holes don't just warp space, they warp time. The stronger the curvature, the slower time flows for a clock within that region. This is gravitational time dilation at the edge of the event horizon. From the perspective of a distant observer, the time of an infalling object slows until it seems to stop completely. Imagine you drop a glowing clock toward a black hole. From your vantage point, the light signals from the clock would become redder and redder, their wavelengths stretched as they struggled to climb out of the deep gravitational well. The clock's blinking would slow and slow until it appeared to freeze just before touching the horizon. Meanwhile, for the unfortunate clock itself, it would notice no special moment of crossing the line. It would pass through without hitting any physical wall right up until tidal forces tear it apart near the center. When a black hole spins, the story gets even stranger. The solution shows that rotation distorts spacetime so much that not only is there an event horizon, but also a region called the ergosphere where spacetime itself is dragged along with the spin. Inside this region, standing still relative to a distant observer is impossible. Everything is forced to co-rotate. This frame-dragging effect is terrifyingly powerful. And in principle, it's possible to extract some of the black hole's rotational energy through a process known as the Penrose process. But before we dive into those subtleties, let's solve a more practical puzzle. If black holes are black, how do we know they even exist? In the 1960s, when the idea of black holes was still met with skepticism, astronomers discovered a powerful X-ray source in the constellation Cygnus, naming it Cygnus X1. It was intensely bright in X-rays but optically invisible. By the 1970s, by tracking the motion of its companion star in the binary system, they deduced the mass of the invisible object to be about 15 times that of the Sun, far too heavy to be a neutron star. Cygnus X1 became the first convincingly identified black hole candidate and opened up the path forward to see the invisible. Watch its effect on the visible. Today, we recognize black holes by the halo of light emitted from their accretion disks. Matter pulled in by gravity rarely falls straight down. The conservation of angular momentum forces it to spiral into a disk, where friction between layers of gas heats it to millions of degrees. At that temperature, the plasma emits X-rays and sometimes even gamma rays, high-energy screams that allow space telescopes like Chandra and XMM Newton to hear a black hole from across the galaxy. By analyzing the spectrum and flickering of this radiation, we can infer the black hole's mass, spin rate, and the extreme physics just outside the event horizon. Beyond accretion, astronomers sometimes have the chance to directly weigh these ghosts. At the center of our Milky Way, teams led by Reinhard Genzel and Andrea Ghez tracked the star S2 as it orbited a compact radio source named Sagittarius A. S2 completes a highly elliptical orbit in just 16 years. At its closest approach, it travels at nearly 3% the speed of light. There is only one way to explain this: the existence of an incredibly compact object weighing about 4 million solar masses, confined to a space smaller than Mercury's orbit. If that isn't a supermassive black hole, what is it? Then, in 2015, the universe spoke in a new way through ripples in space-time itself. LIGO detected the first gravitational wave signal from the merger of two stellar mass black holes. The chirp waveform, where frequency and amplitude increased just before cutting off, was a perfect match for simulations. In that fleeting moment, about 3 solar masses were converted entirely into gravitational wave energy. ERMC2 releasing more power than all the stars in the observable universe combined, a truly goosebump-inducing figure. Since then, hundreds more mergers have been recorded, turning gravitational wave astronomy into a new window for studying black holes. And then, the dream of seeing one became a visual reality. In 2019, the Event Horizon Telescope EHT, a global network linking radio dishes from the South Pole to Hawaii, released the first-ever image of a black hole's shadow M87 OS. It wasn't the event horizon itself, but the silhouette cast by its gravity bending the path of light, a dark central region surrounded by an asymmetric bright ring of superheated plasma just outside the horizon. The size and shape of that shadow were a stunning match for the predictions of general relativity. In 2022, our own galaxy's SGRA was also imaged, though it proved more complex due to its rapid variability. From Cygnus X1 to S2, from LIGO to the EHT, the pieces of the puzzle all point to one reality. Black holes are real, and they behave just as Einstein described, at least, up to the edge where quantum physics begins to speak. The next question is almost inevitable: if black holes swallow everything, do they live forever? In 1974, Stephen Hawking proposed an idea so bold it stunned the entire community: black holes aren't entirely black, due to quantum effects in the curved spacetime near the event horizon. They emit an incredibly faint thermal radiation now known as Hawking radiation. This means that black holes can lose energy, lose mass, and, in principle, eventually evaporate. To picture this, we need to abandon the idea that a vacuum is empty. In quantum mechanics, a vacuum is a vibrant, seething state of quantum field fluctuations, the background fabric upon which reality is woven. Even when nothing is there, pairs of virtual particles and antiparticles can pop into existence and annihilate each other in extremely short times, as long as they repay their energy debt according to the uncertainty principle. Near an event horizon, the extreme curvature of space-time can separate these newborn pairs. One particle might fall in, while the other escapes from far away. It would look as if the black hole just emitted a particle, meaning it has a temperature. That temperature is inversely proportional to its mass. Smaller black holes are hotter, while stellar mass or supermassive black holes are so cold, their temperature is practically zero compared to the cosmic microwave background. So while Hawking radiation is currently impossible to observe, in principle, this space-time engine is slowly leaking. The consequences of this idea are profound. If a black hole radiates like a thermal object, that radiation appears to be completely random, carrying no information about what fell in. But quantum mechanics has a hard rule: the evolution of a system is unitary, and information can never be destroyed. So where does the information of a book, a spaceship, or a star go after falling into a black hole that eventually evaporates completely? This is the black hole information paradox, one of the deepest challenges in modern physics, where general relativity describing the black hole clashes with quantum mechanics describing the information. Many ideas have been proposed to resolve this. The holographic principle suggests that all the information contained within a volume of space can be encoded on the surface that surrounds it, like a three-dimensional image generated from a two-dimensional film, applied to black holes. This implies information doesn't disappear inside but is imprinted on the event horizon in subtle quantum bits, and then, somehow, leaks back out via Hawking radiation at the other extreme. The firewall hypothesis proposes that a region of immense energy exists right at the horizon. Anyone falling through would be incinerated, and their information processed in a way that preserves quantum laws but violates general relativity's equivalence principle, the rule stating that a free-falling observer feels nothing special when crossing the horizon. Both paths require us to rethink space-time, quantum mechanics, and the very meaning of inside and outside. While there is no final answer yet, one thing is certain: black holes are not graveyards of knowledge. On the contrary, they are nature's most extreme laboratories, where humanity's foundational theories are pushed to their limits. There, every piece of evidence we gather, from the shape of the shadow measured by the EHT to the waveforms recorded by LIGO, is slowly completing the picture. There are still empty pieces in this puzzle, But those gaps are the most beautiful invitation science could ask for. Black holes are not just lurking dark spots in galaxies on a cosmic scale. They are the engines that shape galactic evolution through a mechanism called active galactic nuclei AGN feedback. When a supermassive black hole feeds, the energy launched outward as powerful jets and winds can blow away cold gas, the raw material for stars, causing the galaxy to age faster and form fewer new stars. A process known as quenching. But in some circumstances, that same push can compress gas clouds and trigger bursts of star formation. In other words, the black hole at a galaxy's center doesn't just reside there. It manages its galaxy's climate, a giant thermostat fine-tuning the life of billions of stars. On a theoretical scale, black holes are the ultimate strong field test for general relativity. The shadow of M87E, its size and circularity, the gravitational redshift of star S2 as it whipped past its closest approach, the gravitational waveforms of two merging black holes, all of it is currently saying so far. Einstein was right, but at the edge, where Hawking radiation whispers about information, science knows there is something more we don't yet understand. The answer may lie in a nascent theory of quantum gravity, a framework that unites general relativity and quantum mechanics under a single roof. If you find the universe both terrifying and beautiful, if you want to continue this journey where time bends and light is broken, then hit like, subscribe, and turn on notifications. Because the beauty of the universe lies in what we don't yet understand, and the journey to understand always begins with a question.